Hello there. In this video we're going to take a look at how we can treat an RLC circuit in a series AC circuit. Alright, so we've taken a circuit we've calculated before, an RL circuit, 100 millihenry coil that has 37.699 ohms of XL and a resistance of 20 ohms in that coil. So what we did is we added a capacitor into that circuit, a 105 microfarad capacitor. So what we want to do then is figure out what is the new value of impedance in the circuit. But this comes as a little bit of a trickier kind of problem, and it relies on your previous knowledge of the following. So when we look at the quadrature power of the two items, we can see that the Q of XC is going to be storing power in the electric field, and the Q of XL is going to be releasing power back into the circuit from the magnetic field. And those two are opposite to each other all the way through, 180 degrees apart. So when one is charging up, the other one is discharging. And when the other one is discharging, this one is charging up. And so they're complete opposites to each other, back and forth, and they can oscillate. So this is something that we need to take into account when we look at an RLC circuit, particularly when we're looking at XL and XC. So this is how we got to do it and put it into our impedance calculation. All right. First thing though is let's go ahead and put in what we know. Okay, so the resistance is 20 ohms. That's the resistance of the coil. And then we have a XL of 37.699. Okay, now when we go ahead and calculate XC, which is 1 over 2 pi FC, we're going to figure out that we have an XC value of 25.26. Okay, so the numbers are quite similar, 37.6 versus 25.26, but when we add them together, they actually sort of have a canceling effect, and their overall X net, which will be the difference between the two, is going to be lower. So I'm going to take 37, subtract 25 off of it, find the difference between the two. We're going to figure out that X net, the total reactance overall in the circuit from the viewpoint of the source, is going to be 12.439 ohms. All right, so I basically took my XL, subtracted my XC off of it, and I know that my XL is larger, so my X net is somewhere up here. And now we have a new circuit property to look at, all right? So we have our R total and our X net total. Now we're going to go ahead and try and find our Z total, which is the new impedance of the circuit. So before, our impedance was up from here to here. It was quite a bit longer, but now that we added XC, it brought down the total X net, and we have a much lower or reduced impedance in that circuit. So we've actually lowered impedance by adding a capacitor in series. So with the values 20 squared and 12.439 squared, take the square root of both of those. With Pythagorean theorem, we'll figure out our new Z total is 25.553 ohms. All right, so you can see our Z total is actually lower than XL. That's because that was canceled off quite a bit, and we only have this 12.4 in total for X net. All right, so that's a very typical thing to come across, and we're going to see the same thing in power as well. So we can find our current very easily. So the I total is going to be the E total over the Z total again. So that's 120 volts, and we're dividing it by 25.5 ohms, and we get 5.1 amps. Okay, so 5.1 amps, an increase in current after we added that capacitor, because we saw the ohmic value, the total impedance, go down in the circuit. So it's exactly what we expect to see. All right, so we'll go ahead and we'll do the power triangle or a power diagram, and we'll see the exact same thing. All right, so power total is going to be I squared times R total, and that's our R total here of 20 ohms. So we get 520.2 watts in this circuit now. So we saw an increase in wattage as well after we added the cap, because current went up, and that is going to drive more watts out of that resistor. All right, so beyond that, we have our Q, the Q of XL, and that's going to be I squared times XL, and that's 980.55 That's vars. Then we have our Q of XC, write that a little higher, Q of XC. So the Q of XC is going to be I squared times XC times 25.26, and that'll be 657.1013 var. All right. Now, to find the difference of the two, there's two ways we can go ahead and find our what we'll call our Q net. So the Q net is going to be I squared times X net, just like it was I squared times XL or I squared times XC. I squared X net will get us our Q net, or we can take our 980 vars, subtract off 657 vars, and that'll give us our Q net as well. So we'll get 323.538. Vars. All right, 538 vars. So we have an overall change in every kind of component in this circuit after we added the capacitor, because impedance changed and the current changed, and basically everything in the circuit changed other than the core values of L and R and the voltage. Okay, so we can go ahead and calculate our new value of S, which is going to be I times E. So we'll take 120 volts times 5.1 amps, or we can take our new impedance and do I squared times Z, so 5.1 amps squared times 25.55. That'll work as well. So both of those are good for finding your S. All right. So I times E, really easy, 120 times 5.1, and we get 612 VA. All right. So that is the power after we added that capacitor. Overall, what we saw is an increase in every factor except for our vars. Current went up, so our watts went up. Our Q of XL went up. Our Q of XC went up. But seeing as they cancel, our Q net may have actually gone down. And if they equal each other, if QXL and QXC equal each other perfectly, then Q net would equal 0, and there'd be no vars from the source being supplied from the source. It would be a purely resistive with a power factor of 1. All right, so that's what you got to do when you're doing an RLC circuit. Then you have to make sure your L and your C are acting against each other and sort of canceling each other out in a way. They still exist, but not from the appearance of the source. They start to kind of disappear from the source, and the source doesn't have the burden of trying to power them. As the inductor is collapsing, the capacitor is charging. As the capacitor is discharging, the inductor is expanding. And so they just work back and forth and oscillate. And most of the work that the source is doing is powering the resistor. We can see that here. 612 VA in total is coming from the source, and 520 of that is powering the resistor. So the rest of this stuff is just oscillation, back and forth between the two components. It's quite interesting, all right? So I hope you enjoyed this video, and we'll see you in the next one.